Yeah, sorry, for some reason the camera just did not turn on. Every previous time had no problems. Yeah. So I have to give a talk for the first year graduate students right after this. So I'm going to keep it. Let's see how far we get before I have a leave for that. So let's get. I focused on these three topics. We may not even be able to finish all of them, but we'll try to get as far as we can in these three topics. So in the last class, we looked at a state, just some general state that I wrote down. And I asked, what is the state after measurement? And we saw, and you all understood that if I measure 0, 0, then it's just 1/2, 1/4, 3/16, and 1/16, just from norm squared of each of those coefficients. And then we also asked, what is the probability to measure 0 on just the left qubit? And we saw that that is just these two states, right? When there is a 0 on the left qubit, and so we got probability of 0 to be 3/4. And after that left qubit has been measured, the new state of the system collapses to this state over here, where there's a 0 on the first, the left qubit, and the right qubit is not fully determined. It could be either 0 or 1 with these probabilities, 2/3 or 1/3, right? So that was what we discovered when we did this calculation last time, and we can repeat that. If we have the state 1, then the only possibilities are these two states, which give you a result of 1 on the left qubit, and then we also did the corresponding collapse, and of course the probability is 1/4, and this is the new state that results when we collapse, meaning after we observe the left qubit, this will be the state of the right qubit. Okay. And we can now also, of course, ask, and I asked you to go back and check this. What happens if instead we chose to measure the right qubit first and found it to be in the state 0? Did anybody carry out that calculation? What happens if you measure 0 on the right qubit? And what is the probability? Yes?
Like 11/16 when I squared like
yes.
leftmost and one over there.
Excellent, very good. Yes, it is 11/16. And then what is and then obviously the other one was the 5/16, right? Did you find the state after?
Yeah, so we just have to take the two terms to the 1/2, 0, 0.
0, 0, yes.
And we take the radical 3/4. That one, we bring that down, and we just have to fix that.
Very good. Excellent. Everybody follow that? Right? Okay. And of course, then you can carry out the same thing. So I should have written down the state on the PowerPoint, but so just so you can verify the state. Well, if you have problems, ask me and I'll write down the answer. Or maybe I'll put the answer on the slide before I post it or something. Just remind me if you still need the answer or something and I haven't posted it. But I think hopefully you understand what to do now, right? Everybody is okay with that? Do you need me to go over it? 0 and 1 on the right qubit instead? If you do, there's no problem, I can do it. Okay. I'm not hearing any requests, so I will move on. Feel free to ask me later. Okay, we can extend this to any number of qubits. So here is a 3-qubit state, right? And now instead of writing actual numbers, I'm just writing some coefficients, C0, C1 up to C7, like we discussed last time. What is the probability to measure 0, 0 on the left and the middle qubit? That is, the left and the middle both have to be 0. What is that probability? Can you tell from this state? Yes?
just in the same thing we did before.
Yes.
So 0 or C0 and C1.
Excellent. So C0 squared plus C1 squared. Very good. And what will be the state after that measurement? Yes?
We just take that C0 and C1 and then just normalize them.
Excellent. And the normalization will be exactly the square root of that probability that you just found out, right? So what I mean is. Exactly. So that is correct. And this is a common thing that will occur. You might have already noticed this pattern with the 2-qubit states that we were looking at. That the constant, the normalization constant that you find is always the square root of that probability, or 1 over square root of that probability to be in that state, which makes sense, right? Because we know when we are projecting it, it has to now have a new probability. So that whole state psi, the C0, 0, 0, 0 plus C1, 0, 0, 1 plus blah, blah, blah. And now we measure 0, 0 on the left and middle. Then the right qubit is still undetermined, right? We know that it must therefore be this state, 0, 0, 0 plus C1, 0, 0, 1, like you pointed out. And now you have to divide by the normalization, which is simply C0 squared plus C1 squared. And as you just said, the probability for this 0, 0 left and middle is also this term here, C0 squared plus C1 squared. So that normalization constant is always that 1 over that square root of the probability to be in that state. Okay, so what happens if instead of measuring the qubits one after the other, what happens if, like so far we were measuring like say 0, 0, right? Or 0, 1. But what if we measure the qubits sequentially? Okay, so what I mean by that is, which is, after we have measured the left qubit in that 2-qubit state, let me write it down again. So what happens if, so the probability for the left to be in 0 or that 2-qubit state was 3/4. Okay, and after that state, well, let me check here. What's that? We just write down. Yes. So after the state was after the left qubit in the 2-qubit state was measured, we saw the probability was 3/4, and we saw that the state after the collapse, or after the left qubit was measured, be in the state 0 was square root 2 over 3, 0, 0 plus 1 over root 3, 0, 1. Okay. So that means that now the probability to be, so what is the probability now for the right qubit to be in the state 0? Aware of that? So 2/3, yes. So then we can say probability for left equal to 0 and right equal to 0 is probability equal to 3/4 times 2/3, right? Which is 1/2. And if you look back at the state, the coefficient in front of the 0, 0 the state itself was 1 over root 2, which means squaring that would have given you 1/2, which makes sense. So what this is saying is, if I measure the left first and then the right, that's equivalent to measuring them both simultaneously, measuring both left and right. As long as nothing was done to this state in between. That's of course important to remember, right? We measured in the left qubit, and then we waited some time and measured the right qubit. Well, if something happened to the state in between, then of course this no longer applies. But if we don't do anything to that state, then this is indeed the same probability, okay, as measuring them both at the same time. Okay, 0, 0. Okay, we can do this for all the remaining states. I'm not going to go through that. I encourage you to just follow that up. It's for each of the remaining states, that is, when you measured left to be in the 0, which is 3/4, we can certainly do what about the measurement for the 1/3? That is just 3/4 times 1/3, right? And that will be 1/4. And again, if you check the number, it'll be 1/2 squared, which was the coefficient in front of the 0, 1 state. And when I put it up on the slide now, you'll see that. Okay. Of course, the question is, what if something happened in between? For example, we know from many previous examples when we did with single qubit, if we rotated the basis in between and measured it, something different can happen, right? So that has to be borne in mind, but this is just to show you that all of these different measurements are consistent. And we'll come to how to handle those intermediate situations as well. So yeah, so this is that state again, and as I just said, probability to be in 0, 0 is half, probability to be in 0, 1 is 1/4, just by directly squaring those coefficients. Okay, so that was just what we just saw. And maybe by now I don't think I need to tell you how important the rotated basis measurements are. We saw that again and again, whether it comes to like bomb detection or that or the imitation game where Alan was trying to like imitate quantum circuits. Every time rotating the basis screwed up our normal classical calculations. Like our normal way of thinking really gets all screwed up as soon as you start to rotate the basis and make measurements. And we saw that that could be useful, for example, with the bomb detection. And of course, we then want to be able to do the same things now for these qubit states, the multi-qubit states. But you can see it's going to be rapidly quite difficult, meaning not difficult in terms of conceptually, but the algebra is going to get fairly, long very quickly. If I go back to this state here, and if I ask you now, what is the probability for the left qubit to be in this state plus? What would you have to do? I want the probability for the left qubit to be in the state plus. Yes?
We have to, I don't know the right terminology, we have to like convert the basis so they're all like plus or minus.
Yes.
And then we can measure it.
Yeah, so the one way to do that would be rewrite all the zeros in terms of plus and minus, in the first qubit alone, right? Just the first qubit alone. Rewrite 0 as 1 over root 2 plus minus, 1 over root 2 plus minus, 1 over root 2 plus minus, 1 over root 2 plus minus. So that's the conversion from a 0 1 basis to plus minus basis. And then do all the algebra, right? I mean, there's a bunch of terms, and then pick out only the terms with plus in the first position. And then you have to repeat this for minus, and then you have to repeat it for the other two. So you can see it rapidly gets complicated. The other way, which we have introduced now a few times, is to act on this state with the plus state from the left. That is for only the plus qubit with a bra, right? Because as you may remember, the bra state projects the entire state onto just that particular state. Do you know what I'm talking about? If not, you can stop me here. We will come back to it again also when I introduce the projection operators, but I want you to start becoming used to doing that way instead of trying to, because the way you mentioned will work, but it's extraordinarily long. Okay, it'll take you a long time. Instead, if you think in terms of these bra operator from the left, coming in and taking, eating up all the plus states on the left-hand side, right? So the bra from the left, that number that you get will be the coefficient that gives you the probability to be in the plus state on the left qubit, and leaving the right qubit untouched, of course. Okay. So we will do some examples in a little bit, but it's important to see that you can do it with the Ket algebra, and the way to do it is by operating with the bra vector plus on the left-hand side, and then in linear algebra, as we'll see, it becomes a little bit easier as we start doing these operations. So yeah, and of course, we could have some other basis, plus y, minus y, or when we did, for example, the quantum bomb detector, we may have some other basis, uv, where u and v are slightly rotated from the 0, 1 basis, and we'll want to know any of those situations, how to do the measurement. Okay. Okay, we will come back to this and see how to write it properly. Okay, so now I'm going to introduce the famous concept of quantum entanglement. This is our first pass through quantum entanglement. We are not going to be covering all the properties of quantum entanglement here, but I want to introduce it and introduce the language and give you a couple proofs of what quantum entangled states are. Okay, and we'll have to rediscover this. This is a very deep topic, so we'll come back to it again and again. Okay, but here's the first introduction, first pass. All right, so we can easily show that there are many qubit states, 2-qubit quantum states, that can be factored into tensor product of the individual qubit states. What do I mean by this? So here, for example, is one such state. You can see, looking at this state, it's 0, 0 minus 0, 1 plus 1, 0 minus 1, 1. It's not immediately obvious, but it can be written as this tensor product state. What I mean is, each individual qubit is in a state, and you just multiply them together by the tensor product. Does that make sense to everyone? We can essentially separate out the state into two states, one for this qubit and one for that qubit. That is measuring this qubit. So if I measure, say, this guy into the state 0, right? Well, yeah, it will project this state qubit into the state 0, but will leave this state untouched, right? Because nothing happens to this qubit. This qubit remains in the state 1 over root 2, 0 minus 1, which is very different from that earlier state I wrote down. The state we wrote down and I have been discussing in the last few slides, the one for which we, each time when we measured 0, it projected the other qubit into a different state, right? Either 0 or 1, it projected that qubit into a different state. Here, it doesn't matter whether the first qubit gives me 0 or 1. The other qubit will always remain in the minus state, 0 minus 1. Is that clear to everyone why that is true? No? Well, think about what will happen when I measure the first qubit. Will anything change to the second qubit?
Yeah. From the first stage, it will go to a different block.
It will go to a different state, but what happens to the second qubit? What state is it in? You're not sure. So if I measure 0, 0 plus 0, 1, let's take this state first. Very simple state. What happens to this state when I measure the first qubit? And I find it to be in 0. It remains the same.
Yeah.
Right? So I can write this. Remember what this is. This is a short form for 0 tensor 0. Remember the two qubits are in different spaces, Hilbert spaces. Okay. So I can rewrite this whole thing as 0 tensor with 0 plus 1. Divided by root. Do you agree with that? With that statement? Okay. So if I measure this qubit and find it to be in the state 0, the second qubit is in the state 0 plus 1 over root 2. Okay. That's guaranteed by this construction. So it doesn't change. The second qubit remains in the state 0 plus 1 over root 2, irrespective of what happens to the first qubit. Qubit can be measured, it can be rotated, it can be, anything can be done to it. I could measure this in the state plus. Let's say I measure in the state plus, right? State plus is I project with the bra operator plus, bra vector plus onto the first qubit. Okay. Well, this will give me something, right? It will be probability half that it's in the state 0. It doesn't matter. Or it can be probability half that will be in the state 1, right? Okay, I'm sorry, in this case it's 0 and plus, so there's only one possibility. It's a probability half to give me 0. But the point is, I can do anything I want here. I could rotate this first. I could apply a single qubit gate on this guy, some R, do whatever I want to it, and measure it after that. And I can do any kind of thing in here, nothing will happen to this thing. This will remain always 0 plus 1 divided by. If I measure this in the state plus, it will always give me this. It's as if it doesn't know what's happening to the other qubit. It doesn't care, right? Does everybody see that? No? So, no surprise, these states are called separable or products. Okay. But if you go back and look at the previous example that we just did, those state clearly affects whether the state is the first qubit is in the state 0 or the first qubit is in the state 1. That clearly affects what happens to the second qubit. Okay, so there's a clear difference between these two. So, in fact, from what I've just told you, you can see I could think of the two states as being in two separate block spheres. So one state is in some plus or minus state. In fact, in this case, it's in the plus state. So it's all pointing along the x-axis in the block sphere. Whereas the other one is along the minus state in its block sphere. Remember, these are two separate block spheres, one for each qubit. Okay. So the two block spheres don't talk to each other. And I already told you it's sort of impossible to visualize the most general state of two qubits already. So the fact that I can write them as two block spheres separately tells you already that this is a more simple state, something that we can understand more easily. So these states are called separable or product states. Okay. So they're just like the two qubits don't know about each other, don't care about each other. They just live in their own happy life and ignore the other one. So let's do an example. If I just gave you a state though, it seems like it would be fairly difficult to figure it out, but I'll show you now that you can actually figure out how to factor any general state. Okay. You write the state down and then I can erase it. Okay, so we want to factor this state. What do I mean by that? I want to write it as the product, the tensor product of two states, A 0, 0 plus B 0, 0. To be maintaining our notation. So the left qubit is the 1 qubit and the right qubit is the 0th qubit. Everybody see that? They are claiming that we can write it like this. And now I have to find the coefficients A1, B1, A0, B0 that will give me these states over here, these numbers over here. So the direct way to do this is to multiply this out and find the answer. I'll show you a way which is using linear algebra because that's also equally useful to know. So if I write this as column vector, it's the column vector A1, B1, right? That's the linear algebra representation. Tensor product with A0, B0. Okay? And this tensor product, we can write this as A1 multiplying A0, B0. So that's A1, A0, A1, B0. Then B1 multiplying the same vector over here. So that's on the right hand side. Okay, the right hand side is this column vector, and the left hand side is just the same column vector, but with the coefficients that we have been given. So root 3 divided by 2 root 2 minus root 3 divided by 2 root 2, 1 over 2 root 2, and minus 1. 2. I guess I could have kept the 2 root 2 outside just to make it a little easier to read, but it's there. So you see the left hand side and the right hand side have to be equal to each other. So that gives us 4 equations. Notice I have to be careful about the ordering 0, 0, 0, 1, 1, 0, 1, 1. I have to pick those coefficients carefully. Make sure I don't match the wrong coefficients with each other. So the way it's written down, and I generally won't try to trick you, but when you are writing down your own states, be careful, be sure to write them in the right order. That is 0, 0, 0, 1, 1, 0, 1, 1. You have to make sure of that, otherwise you get the wrong results. Something that can trip you up quite easily. So anyway, so A1, A0 equals root 3 over 2 root 2, and B1, A1, B0 equals minus root 3 over 2 root 2. So I can take the ratio of these two equations, right? So 2 divided by 1 will eliminate A1 from these two equations, right? I'll get B naught divided by A naught equals minus 1. Okay. And similarly, we can do B1 A naught equals 1 over 2 root 2 and B1 B naught minus 1 over 2 root 2. Okay. So from this, actually, yeah, we're already done actually almost. So we know B1 equals now 1 over 2 root 2 times A naught from this equation, right? And substituting B1 into this guy, okay, and using the fact that B naught equals minus 1, you just get minus 1 over 2 root 2 equals minus 1 over 2 root 2. So that gives you no new information. Does that make sense? So this equation is basically does not give us new information, but with these three, we can now solve this problem. So we have from this equation A1 equals root 3 over 2 root 2 A naught. Right, so I solved for A1 from this first equation, so that's root 3 over 2 root 2 A naught. And this one is minus A naught, so that's minus A naught times minus A naught times okay, let's write this. A1 equals root 3 over 2 A naught. B naught equals minus A naught. Okay. And B1 was 1 over 2 root 2 A naught. Very good. So we have three of the coefficients, A1, B naught, B1, written in terms of the other coefficients. And we know we have to have overall normalization. So that gives us another condition. So we know that we have essentially solved this problem. So let's see if I can not erase this. So if I substitute now for A1 and B1 from here, I get that right-hand side over there, the RHS equals 1 root 3 over 2 root 2 A naught times 0 plus 1 over 2 root 2 A naught times 1. Tensor product with A naught state 0 and B naught was minus A naught. So that's minus A naught state 1. So the A naughts cancel out, right? And this is equal to the states 3 over, or just take 1 over 2 root 2, root 3 0 plus 1 plus 1, tensor with 0 minus 1. If I want to now write this as like an actual qubit state, then we know that this one has to be normalized, right? So I need to write this, and I have a root 2 nicely sitting here, so I just take it over here. So I get 1/2 root 3 0 plus 1, tensor with 1 over root 2 0 minus 1. So I've shown you by explicit factorization and solving those coefficients that I can write that that state that looked like it might be something complicated. I've shown that I can write it as just a separable state, meaning it's a product of two qubit states, one for the left and one for the right. Okay. Any questions on this procedure? Yeah, every time it requires a little bit of thinking. Yes.
Yeah,
Did I erase what you needed?
no,
Oh,
on
okay.
the other board.
Yeah,
I was,
the other board.
why did you go 1 over square root of 2 again?
No, I did find this other. So there's no reason specifically I could have left it like this, but if I want to write it as like a nice qubit times qubit state, I know I need to normalize this right-hand side. So I would have ended up, basically having to divide that by root 2 to normalize it. But I already have a root 2 sitting here doing nothing. So because it's outside, right? It's common to everything. It's a common factor. I could have even gotten rid of this factor in some sense. But then I would have had to normalize this state and this state, I would have ended up with exactly this factor.
Okay.
So yeah, if I drop the factor 2 root 2, then I'd have got root 3 0 plus 1 times 0 minus 1. So that's a separable state, but it's not a qubit state yet. because each qubit needs to be normalized. And so I ended up dividing by 2 root 2 in the end. Yeah. So of course, the state was set up nicely in the beginning so that all these factors come out. Not every state that you get in the wild, so to speak, is going to be like that. Then you have to carry out the normalization yourself. Okay. And now that we've done that for one state, I think you'll understand that a product state of n qubits, or now that we've done for 2, we generalize to n right away, which is that any product state of n qubits can be written as some product of each of the individual qubit states, tensor product. Okay. And so we only need 2 n complex numbers to describe this state, right? Each of these qubit states is 2 complex numbers. There are n of them, so you need 2 n complex numbers, which is just polynomial in the number of bits or the number of qubits. So it's a polynomial complexity for this state. And if quantum computers only use such product states, then they could easily be simulated by a classical computer, a universal Turing machine, right? Because it would just fall under the P, that is BQP, basically would be inside P, if that were true, if this were true. And we know it's not true, because there are states that we can write down during a quantum computation that don't follow this pattern. Okay, and that brings us to entangled states. There are many 2-qubit and n-qubit states that cannot be factored into tensor product of individual qubit states. For example, I claim that the state 1 over root 2, 0, 0 plus 1, 1 is not equal for any choice of coefficients to this state, A1, 0 plus B1, 1 plus A0, 0 plus B, this should be plus B0, 1, okay, not minus. So, was it a minus on the previous slide too? Just didn't notice. Oh, yeah. No, that one is correct. Anyway, okay, yeah, doesn't matter. Okay, so, and the point, of course, is we cannot visualize the state as 2 block spheres with each qubit represented by a point on the individual block spheres. Okay, there's no way to kind of take out one of the qubit states and just think of the other, each of them as individual qubits with their own qubit state. Okay, so of course now I have proved to you that this cannot be written in this way. Okay, so here comes the proof. And you will follow this because we have now done an example where we factored a qubit, therefore a qubit state, therefore the proof is by contradiction. Okay, we're going to assume that we can indeed factorize that state that I wrote down into the product of 2 qubit states, and then I'm going to show you that that leads to a contradiction. I'll leave this part up here because it follows directly from the proof. I should have left everything up here except for the state. So the claim is that if that state 1 over root 2 times 0, 0 plus 1, 1 be written in this form, okay? We claim that it can be written in this form, and we show that that claim leads to a contradiction. Okay. So on the right-hand side, I'll just write this right away as that column vector. Okay. It's A1, A0, A1, B0, then B1, A0, and B1, B0. Okay. Already this will suggest to you something interesting, which is true for all product states. That is, if I take this coefficient over here and multiply it by this coefficient down here, so I pair up the first and the last coefficient, okay, that is what? A1, B1 times A naught, B naught, right? Everyone agree with that? If I multiply these two coefficients here, it's A1, A naught times B1, B naught, okay? And these two coefficients in the middle, so multiply these two, that gives me A1, A naught, B1, B1, B naught, okay? So basically A1, B1, A naught, B naught, okay? And I multiply these two together over here, that gives me A1, B naught, B1, A naught, which is also the same as A1, A naught, B1, B naught, okay? So these two products have to be equal for a product state. Does that make sense to everyone? Okay. So therefore, by contradiction, all I have to do is show you that this state doesn't satisfy that constraint. Okay, so let's look at this state. Okay. So it's 0, 0 on top, so that's 1 over root 2. And then the 0, 1 state, that one is 0. The 1, 0 state is 0. Then at the bottom, this is 1 over root 2 times 1 over root 2. Okay. So you can see the product of the top coefficients, the first and the bottom, the top and the bottom coefficients is 1/2, but the middle two is 0. Therefore, this state does not satisfy the constraint that the product of those two is equal to the product of the middle. Okay, and this is the proof. That's it. That proves that this cannot be written down as a product state. This is therefore what we call an entangled state. Okay. Your book has a slightly different proof. So you can follow that as well. It's equivalent. I just like this because there's a nice symmetry here. It gives you a nice symmetry and it allows you to check any state, basically. If I claim to you that I give you some state, some 2-qubit state, right away, you can just verify this claim by looking at the top and bottom and the middle two and seeing if their products are equal. Okay? Any questions? That's a proof for the 2-qubit state. And now the general entangled state, right, of n qubits, we've written this before when we first introduced the notation for n qubits, which is just sum j equal to 0, capital N minus 1, where n equals 2 to the power n, small n being the number of qubits. And that's written as C0, 0, where here this 0 means the decimal representation of the binary string, 0, 0, 0, 0, okay, up to n. And this one is, of course, then the same one with all ones in the binary string, right? Everybody okay with this notation by now? What this notation means? I'm not talking about 1 qubit, don't be fooled. I'm not talking about 1 qubit with n states, right? Or one something, qnit, which has n states. It's n qubits, small n, which can be in any one of these states. And that will be a column vector with C0 up to Cn minus 1, which is 2 to the n amplitudes to describe. We need all 2 to the n amplitudes to describe, or in general, the most general qubit state would need 2 to the n. We don't know that every entangled state needs it, but certainly for these. Oh, one thing I should point out about this state here. The state 0, 0 plus 1, 1 is a very special state. Okay. This state here, 0, 0, this state here, 0, 0 plus 1, 1, is one of 4 possible states in the 2-qubit space, which are called maximally entangled states. Why are they called maximally entangled? So go back to our earlier discussion. So let's say we had a state C0, 0, 0 plus C1, 0, 1 plus blah, blah, blah. Okay, let's just take the 2-qubit case for now. And let's say I measured left qubit B0. Then we know that collapses the right qubit to the state, so collapse the right qubit to the state, C0 with now 0, 0 plus C1, 0, 1. You see, this is a product state because the 0 is common to both of these states. So this is a product state of 0 times C0 plus C1 divided by square root C0 squared plus C1 squared. Yeah, we saw that for the n qubit state, and so I just written it for the 2-qubit state. But you see, this new state in terms of the second qubit, the qubit on the right, there is still some uncertainty. Meaning, when we measure the second qubit, we don't know which state it is here. It could be either 0 or 1 with those probabilities. Okay? Everybody okay with me on this? Or no? Stop me if you're not. You're not. You're not sure.
I couldn't follow what you said.
Okay. So imagine now that I measure the first qubit, the left qubit. Then we know by the same argument we had for the n qubit state, it collapses the entire system into this space. That is, it's a system whose first qubit is 0, but the second qubit can be either 0 or 1. Correct? And the probability to be in either 0 or 1 is given by norm squared of these coefficients. But if I look at this state over here, the 0, 0 plus 1, 1 state, when I measure the first qubit to be in the state 0, that collapses the second qubit also. As soon as I know that the first qubit is in state 0, I know immediately what the second qubit is. It is also 0. Or if I measured the first qubit and got 1, I immediately know what the other qubit is. It's in the state 1. These are called maximally entangled states for this reason, because there's no uncertainty at all. Like after I measured the state 1, the left qubit, I immediately know the right qubit state. And same, for the other case. So measure the right, I'll know the left immediately. Okay? Unlike these states. These are the most general states, but they don't necessarily project onto the other state, the other qubits, into a definite state when they are measured. Okay? But these are called maximally entangled states for that reason. And they have a special name. They're called the Bell state, okay, or the EPR state. Okay. This is one of 4 possible such states. I'll write down the others in a minute. Okay. What is so special about these states? Well, John S. Bell was a famous physicist, and EPR stands for Einstein, Podolsky, Rosen. Okay. So when quantum theory was first, invented, and people were talking about what are the implications of quantum theory, Einstein hated quantum theory. Okay. He thought that it was crazy that things didn't have definite properties until you measure them, because this was the interpretation of people like Bohr, and various other people, that until you measure the qubit, it is not in any known state, and we can't even talk about its state. This is what Bohr and people said. And Einstein didn't like it. So he wanted to show that there was some contradiction, some paradox in quantum theory. And he came up with these states, along with Podolsky and Rosen, to try and show that there is indeed a paradox. And we'll get into this paradox later on. But the basic, and then Bell came along and said, actually, we can make this paradox, we can make it testable. Because, the way Einstein EPR said it, it was kind of like a paradox. Okay, something interesting, but nobody can ever test it. But Bell came out and he showed that there's a deep connection to various ideas. He showed it not just for one model, but for a whole class of models beyond what EPR were discussing. He showed, oh, sorry, you had your hand raised. I'm sorry, let me.
Yeah.
Unrelated question. Okay. instead of getting too much into this, when we discuss the EPR paradox, I'll explain it in more detail. But just know that these states, and actually I can write the other states down as well, which are the maximally entangled states. So just so you have it in front of you once and for all. Yeah. Which is the states, and they are given this sort of symbol, phi plus minus is equal to 1 over root 2, 0, 0 plus minus 1, 1. And the capital letter psi, the Greek letter psi plus minus, which is 1 over root 2, 0, 1 plus minus 1, 0. Okay, so these four states are called the Bell states, four Bell states, and they are all maximally entangled states. As you can see, measuring one immediately tells you what the other qubit is doing. And so these are part of the sort of the one of the states that you could use for a EPR, a paradox experiment, for example, or Bell experiment. Sorry, well, what was your question?
Yeah, so once you have a set of qubits that are entangled like this,
Yeah.
possible to split them apart again into a set of one where they permit the six entangled state.
You mean to say, can you split them apart into qubit states?
Yeah,
Or
right. Like right now, we know that it's no matter how we look at it. We
Yeah.
find that the first qubit is 0. We know the second one is 0. That first one's a 1. The other one.
Mhm.
Is there any sort of rotation or transformation
Yeah.
we do to it that would convert it not be entangled? No.
yeah, so that's another theorem that I don't think I'll have time to prove today, but I'll come back to it, which is the same result holds if I had written this as plus minus plus minus plus or minus minus in this case. So the equivalent in the plus minus basis, right, would be this is plus 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 minus minus, right? That is the equivalent transformation. Yeah, exactly. That is the beauty of entanglement. Yes.
So, in the viewpoint of the quantum computation,
Yeah.
does these states have any values? Because you know, when you measure one of the qubits, the other
Yeah.
one's so it doesn't have any extra information to use two qubits instead of one.
Oh, that's a very good question. So I think we have to separate out the various questions here. So does it have more computational power to have entangled states than it is to have non-entangled states? I think that is still, there is, I mean, we know that in the quantum computer, there are entangled states. And in the end, they are, read out through some mechanism, through some gate, for example. Just trying to make, so I think in terms of so I would have to say, yes, the answer is yes. There is some computational power to having entangled states over having non-entangled states. But I don't know if this was your question, whether you're storing more information in that entangled state. And I think the answer is no. Meaning that there are only n bits of information being stored in the entangled state. There is a theorem, I think, by Holigo, who proves that n qubit entangled state has the same number of bits of information, which requires some information theory concepts, but which we won't get to discuss. But it's not true when you communicate. So it's a different story if you communicate entangled states, which we will come to in a minute, in a while, not in a minute, but so there's a difference between computation and communication. Okay, and the communication of an entangled state allows you to transmit effectively more than one bit of information, which is kind of a cool result if you think about it. None of these are statements that I can prove to you in this class, so definitely take the graduate quantum computing class for that. We will try to prove the rotation question that's a very good point and very important point to understand. Okay. Okay. I won't get into too much more here today. Let's see, quantum gates. We don't have time for this. Okay, maybe a couple slides. I'll try to get this done. All right. At least we'll introduce it. Okay, so this statement, I hope everybody is okay with, right? The exponential number of amplitudes to describe entangled states. So we want to now introduce quantum gates, but now these are quantum gates on 2 qubits. Okay, but I'll call them as 1 qubit quantum gate, meaning that we want a gate where we apply a single gate, call it whatever you want, H, X, Y, Z, etc., on the first qubit, but leave the second qubit untouched. So that's why it's a 1 qubit gate. Okay, even though there are 2 qubits in the state. The state is still, you have to describe it as n qubits or 2 qubits in our case, but the gate by its nature acts only on one of them. So 0, 0 is our starting state. Let's just start with that. And we want, let's say, as an example, Hadamard H on the left qubit and leave the right qubit alone. So how do we do this? Any thoughts? How can I operate on the left qubit but leave the right qubit untouched? Yes.
So if these are products, they can separate out. Just do the Hadamard gate on one of those.
Yes.
Parts.
Exactly. Very good. What if it's not a?
Then you can't do it.
Can I still write down a gate that will do that operation, irrespective of what the input state is?
Yeah, but.
Yeah, we can do that, right?
Yeah.
So what is that gate?
Is it just like a bigger Hadamard gate or something?
Bigger atom. Yeah, very good. Bigger how? You're getting close. Yes. Yeah.
You add on identity gates.
Identity gate. Add on. What is add on in our notation?
So the way it would work, so you have like in linear algebra definitions, you have like the 2 by 2 Hadamard gate, and then you have in the diagonal corner you have zeros, and then the bottom right corner you have an identity gate.
Close. Yes, very close. And there's a word for this. We've already introduced this word or introduced this operation. Anybody else want to guess? Maybe somebody else. Somebody else want to guess what that operation is? You're smiling. You know it? That's okay. I didn't mean. I like putting people on the spot, so ignore me. But there is a name for this operation which we've already introduced. For what happens when I take one thing and I somehow multiply it with the other thing, but they're operating in different spaces. Yes.
Inner product.
Inner product. Close.
Tensor product.
You're going to go through all of them. You just go through them. Yes, tensor product. Exactly. Or Kronecker product. So Kronecker product or tensor product, which is H. You should know this, okay? Please make sure you understand this. H tensor I is exactly that gate, because it, as you said, it on the left qubit, it'll do a Hadamard. On the right qubit, it'll leave it identity. Okay? And the way we want to think about gates is irrespective of what's coming in on the input side, right? Because we want the gate to work no matter what's coming in on the input. It could be a product state, it could be a entangled state, whatever it is, it should just do its thing. It should give a Hadamard on the left qubit and nothing on the right qubit. Okay, so we want to construct this gate, and the way we do it is by finding out what it does to each of the possible input combinations, because quantum mechanics is linear, right? So or quantum computing, linear algebra, everything that we've been describing is all linear. So if we know what H tensor I does on 0, 0, 0, 1, 1, 0, and 1, 1, which are the only 4 possible inputs, then any linear combination of them, because that's what a general entangled state will look like, or general 2-qubit state will look like, will just be obtained by just linearizing that whole thing, taking, all of those different products. So let's go through this. So as we just said, H tensor I acting on 0 tensor 0. This is, I'm going to go through it in sort of pedantic detail, but and then in the end, we can just, quickly compress it into like one simple notation. Is equal to H acting on the left qubit, tensor I acting on the right qubit. Which H acting on the right qubit is just the plus state, and identity acting on the 0 state is 0. Okay? And plus state is of course written as 1 over root 2, 0 plus 1. Tensor with the right qubit being 0. And that is nothing but this same state, which is 1 over root 2, 0 plus 1, tensor 0. Is now I'm going to take this tensor and I'm going to work it into the brackets. So that's 1 over root 2, 0 tensor 0 plus 1 tensor 0. Okay. All right. So let's write that state now on the next slide. So 1 over root 2, 0 tensor 0 plus 1 tensor 0. And that is just our notation, 1 over root 2, 0, 0 plus 1, 0. Okay. Which I can write in column vector form. So remember, I have to put the 0, 0 coefficient on top, the 0, 1 coefficient in the second, 1, 0 on the third, and 1, 1 at the bottom. Sorry, I forgot the 1 over root 2 outside. Okay, so there's a 1 over root 2 sitting out here. Everybody okay with this notation? Okay. Okay, we can do the same for all of the other. Oops. Okay, I see. Okay. Let me just tell you about the notation. I won't go through all the other states today. We'll do it in the next class. But we are going to use the following convention to be consistent with the book. Also with Quark, which is that website that I've told you about, where you can manipulate quantum gates. And also when we get to the IBM quantum programming experience, which not too far away now, I think we're getting to it soon. All of these are consistent, luckily, with the book. So, and the convention that we're going to use is the rightmost qubit is the top row of our circuit. Okay. And then the qubit to the left of that is one row or one wire down, and then the qubit to the left of that is one wire down all the way to the leftmost qubit. So just to illustrate that, so we want to write this as a quantum circuit. So H tensor I acting on the state 0, 0 will be represented by this. Notice how the I acts on the rightmost qubit is on the top. And H, which acts on the leftmost qubit, is on the bottom. Everybody okay? Understand this? Right? Please remember this convention. The rightmost qubit and the gate that acts on it will always be at the top. And then subsequent ones will be one row down. And because identity operator does nothing to the rightmost qubit, we can just replace it by a wire. Okay. So the wire always means transmit the state without doing anything. So that is our qubit quantum circuit corresponding to this gate that we have written down, which is just, as you can see, if I didn't have this qubit at all, this would just look like our one qubits or single qubit gates that we've been discussing in the first sort of few weeks of the class. But of course, we know there's a second qubit, so we have to tell what happens to the second qubit in the whole quantum operation. And we have to describe what happens to every qubit at every step of time, so to speak. At every step of our algorithm, we need to keep track of what happens to all the qubits. Okay, I'll finish up the matrix representation of H cross I. Basically, what we have to do is now work out what H cross I does to 0, 1, 1, 0, and 1, 1, and then we'll put it all together to make it that circuit that he was talking about. Okay, I'm going to stop here. And any other questions? I'm glad to also answer. Anything? Any questions? Not? Have a good Friday. Have a good week.